Hi, and welcome to our ModRef talk. This is joint work with a number of co-authors, some from University of St Andrews, some from York. The work that I will talk about today has been going on for a long time, and it's been incorporated in our automated modeling tool Conjure for a long time, but we wanted to explain how it works in a ModRef paper. Even though it has been included in the tool for a while, it is still quite preliminary in that we didn't evaluate some parts of it fully yet. So we would welcome some discussion about these in the context of the workshop. So let's look at the title first. Our title is, well, contains essence specifications in it. So as opposed to models, we refer to problem specifications written in the language Essence as such. I'll talk a bit more about the distinction we make between problem specifications and CP models. So the main work we are describing today is about reformulating essence specifications. This is slightly different from what we normally do inside of the Essence toolchain with the problem specifications. We often start with Essence and reformulate them into something lower level. In this talk, we will start with Essence and reformulate it into other Essence, right? So we will stay at the level of Essence. And our main goal when we are applying reformulations to Essence specifications will be achieving some sort of robustness. And I'll say a bit more about this as well. The paper explains what we mean by robustness here as well. So, to put it simply, it is robustness against differences in how you can write a problem specification, specifically by Essence specifications written by novice users. I'm going to say towards reformulating Essence specifications because this is preliminary work. Okay, so let me talk a bit about Essence at the start and give you an idea of the kind of features this language allows us. The first thing that Essence allows us to allow the distinction between models and problem specifications is the abstract domains it contains. So these are domains that are not directly supported by a solver, things like sets and multisets and functions and sequences and relations and partitions. So these can be seen as fairly high-level constructs which can be arbitrarily nested. So that point is important because I know some solvers do support set variables, but these will be set variables on integers. Here you can have a set of functions or a set of relations that you are looking for as your decision variable. In addition to having the high-level domains, you can have attributes on these domains. Things like cardinality restrictions, injectivity, surjectivity on functions and sequences actually, count and cardinality of parts in a partition or regularity of a partition can be an attribute as well. So this is important because some of the improvements, some of the reformulations we are making in this work are to do with the attributes. In addition to having the domains and using them to create decision variables, we have a bunch of operators defined on these domains. Things like subsets or union or intersect or other set operators you can think of on sets and other collections that can act like sets. So you could take a function and take the union of two functions, for example. Quantified expressions and comprehensions, specifically over decision variables. So not just a comprehension which can be unrolled, so it is over a static set of values. It can be a comprehension over a decision variable. So you could say, find me a set such that sum of values coming from this set, a function applied to each member is less than a capacity, for example. Things like the inverse for function variables, pre-image for function variables, and the host of a list of other operators as well. For sequence decision variables, we have operators like subsequence and substring, and for relations, we have a bunch of other operators, as well as relation projection, which is similar to how projection works in a database sense. So you have a relation and you can fix certain components of this relation and project some of the components. Okay, so with all of those features, Essence gives us the ability to write precise and short, succinct abstract problem specifications. These problem specifications are then converted to solver-independent but concrete CP models. So a bunch of decisions are made at this point. We start from a high-level problem specification, hopefully delaying a bunch of modeling decisions at this point from the user. A concrete CP model is then produced by Conjure. Then we use a tool called Solver.ro, which allows us to target a number of different solvers as well. Solver.ro is able to natively support a bunch of CP solvers, SAT solvers, SMT solvers, and MIP solvers, and many more solvers via a Minisync backend as well. So it can produce Minisync, and you can support any solver Minisync supports through that pathway. Okay, long introduction. Now let's talk about what we mean when we say specification boosting. So this is a problem statement for this paper. The problem is that novice users can make simple mistakes when writing problem specifications in Essence. These could be in the form of failure to use an attribute, even though the attribute exists, and instead of using an attribute, using a convoluted constraint to say the same thing, or using a relation instead of a function, even though there is a functional relationship between parts of the components, a subset of the components to the rest inside of this relation, or something as simple as using a multiset, but with a max occurrence 1 as an attribute, which would make it a set, really. Our solution that we are proposing here is that we have a collection of specification level rewrite rules to catch and improve these common cases. And the impact of these rules is magnified when the rules are applied iteratively. So you may not really have someone who writes, I have a multiset with maximum occurrence 1. That would be quite silly. Even a novice user may not write that. But they might have a multiset and then a constraint which forces it to only have, to not have duplicates in it, right? And at that point, you know the max occur 1 attribute can be added, and then it creates an opportunity to apply another specification level rewrite to convert that multiset to a set as well. I'll give a bunch of examples. You don't need to see my face there. I think I'm covering part of the example. In this example, we have a function that is declared to be surjective, and it goes from the same domain to the same domain. So it goes from an integer domain 1 to n to an integer domain 1 to n. If you think a little bit about this, you can convince yourselves that such a function will have to be total and bijective as well. If you are covering everything in the codomain of this function, you will have to, and you have the function property that's the same value cannot map to two values in the codomain. It will have to be injective as well, hence total and bijective. So this is just a motivating example. Here's another one where we have a slightly more advanced rewrite going on. So there are two steps. The first step, we have a constraint which uses relation projection, right? So you have xi underscore is for the projection operator, and k. So we are essentially saying this relation is functional in the first and the third argument to the second one. And then this allows us to create a function, a total function, that can represent the exact same set of values, exact same set of assignments to the relation at the top. This transformation is done using a toRelation attribute, and then a second rewrite kicks in, which allows us to get rid of the toRelation attribute and use a function application directly. So going from the first one to the last one actually allows us to change this model and improve the model quite significantly. We have a number of other examples in the paper, so I encourage you to go and read the paper. But I'd like to highlight another example here, which is the case of nested domains. So Essence allows nested domains, and in this work, all the rewrite rules that we have developed work on any domain independently of whether they are nested inside another domain or not. So in this example, you have a set of multisets you are looking for at the top, and after a rewrite, we are able to identify, looking at the constraints, that the outer set needs to have cardinality 2 and the inner set needs to have a maximum occurrence of 3. it is very easy to construct corner cases and contrived examples where this sort of a transformation really, really helps because it cuts down the number of decision variables you will have in the resulting model. So it is clearly in examples and constructed examples like that, it is clearly going to be a win in terms of performance. Having said that, we are planning to improve the set of rewrite rules that we have by studying more of the essence problem specifications that we have and improving them and evaluating in two ways this work and the effectiveness of this work. I suggest everyone to have a look at the paper as well as supporting material and examples for this paper that are hosted on GitHub. If you want to play with Conjure, you can get it on GitHub, and we will be very happy to answer questions during the question and answer session. Thank you very much for listening.